So that's not really a new term, I don't think. We've talked about acids and bases before. We talked about the electrolytes and electrolytic activity of acids. We've used plenty of acids and bases in lab, like hydrochloric acid. But in this chapter, we're going to define more precisely and specifically what makes something an acid, what makes something a base, why is that important, how does that affect the chemistry of them. So one thing that we're going to do is look at the definition of like what makes an acid and a base. And it turns out there's different definitions of what makes acids and what makes bases. So we're going to focus on one that will be the most useful for our purposes, which is like biological systems and things like that. And it's called the Bronsted-Lowry definition. And that's this. An acid is a substance that donates hydrogen ions a base is a substance that accepts those donated hydrogen ions. So accepts hydrogen ions. Now that doesn't maybe make a lot of sense yet. So we'll look at that in context. So what does that mean in context? Let's look at a reaction between two molecules. If you dissolve HCl in H2O, so HCl is actually a gas on its own when it's by itself. If you dissolve that in water, what you get is you get chloride ions, and you get this thing, which we'll talk about more later, called hydronium. It's like water with an extra hydrogen and a positive charge, so it's an ion. Hydronium ion. So what we need to do is we want to look at that reaction and identify the acid and the base. First thing to realize with that is look back at the definitions and realize that those definitions are talking about an action. So they're talking about a role. An acid is a substance that donates H+. A base is a substance that accepts it. So that means that acid-base is not a label that we assign to inherently to a molecule or a substance. We don't say this thing is an acid and it is always an acid. This thing is a base and it is always a base. Acid and base are actually words that describe how something acts in a reaction. So in one situation, a molecule may be an acid, but in another situation, it may be a base. In this particular reaction here, what is acting as an acid? What is donating H+? So we can look at the two reactants and decide which one is getting rid of H+ of a hydrogen ion. The what? The HCl. Does everybody see that? So it starts as HCl, goes through the reaction, and on the other side, it's just Cl-. The H+ has been donated to the H2O. See how it's transferred? The H+ has gone from the HCl to the H2O. So that means that in this reaction, the HCl is acting as an acid because it's giving away its hydrogen. It's donating its hydrogen ion. And then we could also say that the H2O in this reaction is acting as a base. So in an acid-base reaction, we have a transfer of H+. H+ goes from one molecule to another one. So that's how we define acids and bases. It doesn't always necessarily work like that. Molecules aren't always defined in that way. So let's take another example. If we take NH3 and H2O, ammonia, NH3 is ammonia, we make NH4 plus ammonium ion and OH minus hydroxide ion. So now in this example, which one is the acid? The H2O, right, the water. That's the one that's losing its hydrogen. So this one's now the acid, and this one's now the base. So look at those two reactions. Water is a reactant in both reactions, but in one it's an acid, and in the other one it's a base. So that's what we mean by those labels, acids and base, mean a role that something is playing in a reaction, not an identity of the molecule itself. Another thing to know about acid and base reactions is they're what we call equilibrium reactions. We'll get into what that means later in the chapter. But it means they go back and forth. It means that they can go forward, but they can also go backwards. So a lot of times when we write acid-base reactions, instead of just one forward arrow, we'll also have a backwards arrow to show that the reaction can go back and forth. I just realized I forgot to save this. Let's save it so that you can all see it. If we think about that idea that the reaction goes back and forth, that means that we can also start on the right and go to the left. So we can define acids and bases on the right as well as on the left. So let's do that. Back up to that top reaction. If we start on the right and go to the left, which one is acting as an acid? The chloride or hydronium? If we think of the reaction starting on the right and going to the left, which one is donating hydrogen? Hydronium. It's got to, right? Because the other one doesn't even have any hydrogen to donate. So the hydronium is donating its hydrogen, and that makes it an acid. And that makes the chloride the base. What about for the next one down? Which one is acting as an acid going right to left? Which one is donating a hydrogen? Ammonium, right? Because it's going from NH4 plus to NH3 neutral. So this one's now acting as the acid, and this one's now acting as the base. Okay. Now, we did that kind of separately, but if you look at those reactions, they're really related. Notice that the NH3 on the left became the NH4 on the right. What was acting as a base on the left is now an acid on the right. And that's true with everything. So the H2O was acting as an acid. It became the OH minus acting as a base. So acid, base are these kind of like the molecules are related, and they're opposite acid or base on each side of the arrow. So we have a name for that. We call those conjugates. Conjugates are a pair of molecules that only differ by H+. So everything else about them is the same, except H+. So H2O and H3O+, they only differ by H+. So that's a base and a conjugate acid, or an acid and a conjugate base. Let's write that down here. Conjugate acids and bases differ by only H+. So only a hydrogen difference between a conjugate acid and a base, or an acid and a conjugate base. So what's the conjugate acid of NH3? if NH3 is a base, what's its conjugate acid? What would we pair that up with on the other side of the equation? The ammonium, yeah, the NH4. So these two would be paired up as conjugates. So we could say that in a couple different ways. We could, in the context of this reaction, we could say the base NH3 becomes its conjugate acid NH4 plus. But we can also kind of say that in isolation. We can just say the conjugate acid of NH3 is always NH4 plus. So let's define it that way and see if we can figure that out for a few different molecules. A conjugate acid is a molecule plus H plus. And a conjugate base is a molecule minus H plus. And we can set up a table here. So we can say, what's our molecule? And then what's its conjugate acid and conjugate base? So if our molecule is ammonia, its conjugate acid is what we get when we add H plus, which we've just decided is an H4 plus. We add H plus, which means we add both the atom H, but we also increase the charge by +1. So if it's neutral, it's going to go to +1. If it's +1, it's going to go to +2. If it's -1, it's going to go to neutral. So you increase the charge by 1, going from, because you're adding H plus. So you're adding H and you're adding a positive charge. All right, so let's look at the opposite then. What's the conjugate base of ammonia? What happens if ammonia loses H plus? What molecule is left? What's left? You got NH3. You take away H plus. What do you got? You got an H2, right? And what about the charge? Negative, right. So if you take away an H plus from NH3, you've got an H2. And since you've taken away a plus, that has to be negative also. Yeah, that works. Okay, let's try a few more. Water. What's the conjugate acid of water? H3O plus, hydronium, yeah. And what's the conjugate base of water? Yeah, OH minus 1, which is hydroxide. Good. And you can do this with pretty much anything. So we could look at, let's look at a charged one. Bisulfate ion, HSO4 minus. What's the conjugate acid of that? Careful, what's being added to it? Right, so what would it be then? Yeah, so we'd add the hydrogen, which makes this H2 SO4. And what about the charge? It started as -1, and we added H plus, which means we added H and we added a positive charge. So that means it should be neutral, right? Yeah. Okay, so what's the conjugate base of HSO4 minus? take away H+, what's left? SO4, and what's the charge? Yeah. Doesn't stop working here. Come on. SO4 minus 2. So we had -1. We lost H+, so we lose the H, and we go down a charge, lose a positive charge. So you end up with -2. All right, let's kind of see how that works. Sort of. Okay. Let's go on. So the next thing we're going to look at is naming acids. Why just acids and not bases? Well, bases don't really have special names. They're named the same way we name everything else. We'll talk about some of the bases like hydroxides, but they're just named like hydroxides, so we don't have to worry about them as being a separate thing. Acids, however, are. So first of all, let's identify acids. If an acid is generally a molecule that is donating hydrogen most of the time, we usually write the formula of an acid starting with hydrogen. So that maybe isn't true for all acids, but for a lot of the ones that we'll encounter, it is. So that means, how do you identify an acid? You look for that hydrogen at the beginning of the symbol. So HCl, HBr, those kinds of things. HNO3, H2SO4, H3PO4. Those are good ways to pick out acids when you see that hydrogen at the beginning of the symbol. And there's two ways that we name acids. There's what we call the binary acids, which are like this. There's only a handful of them. And you write hydro at the beginning, and then the name with ic at the end, and acid. And these, I mean, we've used hydrochloric acid, so that's probably a common name that you remember. But it also works for the other acids in that category. So like HBr, if you had to guess, what would you call that one? Yeah, I think you got it. Yeah, that's it. Yeah. Hydrobromic acid. Because it comes now from bromium, so this one's hydrobromic acid. What if it was HI? What would you call that one? Yeah, hydroiodic or iodic acid. And HF is hydrofluoric acid. So you get the pattern, right? It's kind of the same for all those. So that's when you just have two things. You just have an H and then one other atom. You can call it that. What if you don't? Well, there's another category of acids called the oxoacids, which are acids with oxygen. And the difference in naming there is you don't put that hydro at the beginning. So for instance, HNO3. What's NO3? What's the ion NO3? Nitrate, right. So we call this one nitric acid. Sort of like it comes from nitrate, so it's nitric. What about this one then? Some of these names, like this one, you could maybe guess, but they don't fit quite as nicely. So what do you think? Anyone want to give it a try? Yeah, this one's sulfuric acid. So you'd think since it comes from sulfate, it would be sulfic acid, but it's not. It's sulfuric acid. So sorry. I mean, it's not my fault. I shouldn't really apologize, but I'm sorry that you have to keep that straight. Sulfuric acid. You want to give that one a try? Yeah, phosphoric acid. Phosphoric acid, well, all these are very, very, very widely used, but phosphoric acid and sulfuric acid are used predominantly in fertilizer production. There's also other kind of unusual uses, like phosphoric acid is the thing that really makes a lot of sodas taste good, like Coke. They have phosphoric acid in them. In the old days, sodas were known as phosphates sometimes, and that's because they had phosphoric acid in them, which has a really nice acidic flavor. It also means that Coke can be used to like clean metal pretty well. Like if you got corrosion on steel wheels and things like that, you can put Coke on there and like scrub it, and it'll just clean it all off, which probably means it's not great for you, but I mean, we all know it's not great for us, so that's fine. And then the actual acid that gives carbonated beverages their carbonation is this one. Anybody know what that one's called? Close. So remember that the ones with oxygen don't get the hydro at the beginning. So it's carbonic acid. What happens in those drinks is you charge them with carbon dioxide. The carbon dioxide dissolves in the water, forms carbonic acid. Carbonic acid is relatively unstable, so then it decomposes, decomposition reaction, and reforms carbon dioxide, and that's where the bubbles come in. That's where the bubbles come up. All right, so those are some acids. The main thing here is, and it's in the objectives on Blackboard, but these few very common acids you should know the names and the formulas for. You don't have to memorize them. The names maybe, but the formulas you shouldn't have to memorize, because you can figure out the formulas by knowing the ions. If you know that sulfate is SO4 and it's a -2 ion, then you know that it needs 2 hydrogens to balance out the -2, because each hydrogen is +1. So if you know the charges of your ions, you can just pair up the hydrogens and get the right formulas. So rather than having to remember, oh, nitric acid only has 1 hydrogen, and sulfuric has 2, and phosphoric has 3, and carbonic has 2, you already know the charges of nitrate, sulfate, phosphate, and carbonate, so you can do that. If we go through all the other ions we know, we can make acids of them also. So what would you call this one? If you took hydroxide and made an acid out of it? You want to give it a try? No? Nobody knows what that is? Somebody knows what this is. What's a molecule with 2 hydrogens and an oxygen? It's water. Yes, it's water. Thank you. Okay, so not really an acid. Sorry, trick question. I mean, it is almost Halloween. It's time for some tricks, right? All right, so we know how to find conjugate acids and bases in an equation. We know how to come up with conjugate acids, conjugate bases, and we can name some acids. So let's take a look at acid-base strength and equilibrium. So I'm going to do this a little bit out of order of the book because I think it makes more sense this way. The word equilibrium just means like things equaling out or things becoming equal. In chemistry, we use equilibrium to talk about these reactions that go back and forth. So when we drew these arrows like this, what we're saying is this reaction, it's not just that you mix these things and it goes and forms these things. The things that it forms actually end up going backwards and reforming some starting material. And this is constantly going back and forth. And in fact, every chemical reaction is technically doing this. It's just that some are weighted more toward one side than the other. So for instance, the pumpkin reaction, the two reactions in the pumpkin, the one here, when calcium carbide and water react to form acetylene and calcium hydroxide, it's true that technically some of it is also going backwards and reforming this. But the energy and the kinetics, the way it works out, it is way more going in this direction than in this direction. Just even anytime you form a gas, that's true because the gas can't really find the other stuff very well because it just spreads out. So every reaction has a little bit going backwards, but this one's almost entirely forwards. Same thing when we burn it, when we lit it on fire. Technically, some of that carbon dioxide and water that's caused by the combustion is also going backwards, but it's not really an important enough amount to make any difference. Almost all of it is combusting and going one direction. We talk about this in this chapter because with acids and bases, often it is really important. And often it's not just as straightforward as we start here and we end up over here. So let me show you a picture, a couple pictures from the book about what these things look like. We can load it up here. So this is page 332 if you're following along. Take a look at this graph. What this is showing is what's happening to the concentration of the reactants and the products as the reaction goes on. So in this case, the red line here is the reactants, and the blue line here is the products. Those little brackets mean concentration. So when you start a reaction, you have all reactants and no products, right? At the very point, like the instant the reaction starts, there's all reactants and there's no products. So then the reaction goes on, and what happens? Reactants decrease because they're getting used up, and products increase. At some point, the products stop increasing and the reactants stop decreasing, and that's what we call equilibrium, the point at which there's no more change. So we can think about it as happening because of the forward and reverse reaction, and a certain amount of it is going forward, a certain amount of it is going backwards, and when the right amount is equal, then you have this kind of a situation. So this is an example of a reaction that we would say mostly goes to the right. It mostly goes from reactants to products because the reactants are decreasing, the products are increasing, and at the end of the reaction, at equilibrium, you have way more products than you have reactants. You see that in the graph? There's more products than reactants, higher concentration, which means that the reaction is trending or tending to go to the right. Other reactions, that may not be the case. And the reaction actually may be more to the left than the right. So in other words, it's going backwards more than it's going forwards. So what happens here is you can kind of control how the equilibrium goes. And a good example of it, or a way to think about it, is to think about two water tanks connected by a pipe. And we thought about this a little bit when we were talking about osmosis. But you've got two water tanks connected together in a pipe. At equilibrium, it's like when the levels even out, right? So what happens if you pour more water in tank A? It balances out until it is even again, right? So the net effect of adding more A is to make a little bit more B. What would happen if you take out water from tank B? What? Yeah, the A would end up flowing over more and like filling in where you took out, right? And the same thing happens with reactions. So if we have a reaction that's at equilibrium, and then we add more reactants, we're going to make more products. If we add more products, we're going to make more reactants. If we take out some on one side, the other side is going to kind of fill that in and correct it. So let's look at an equilibrium reaction as an example. HF, hydrofluoric acid, added to water, makes fluoride ion and hydronium ion. All right, so let's assume this reaction is at equilibrium. The kind of questions we can ask are things like this. What happens to the hydronium concentration when more HF is added? So think about the water example again. Tank A is your reactants, tank B is your products. What's going to happen to the products when you put more reactants in? Is the concentration going to go up or go down? Or stay the same? It's going to go up. Why? It goes up because when you add more HF, you are increasing the level on this side. So when it re-equilibrates, when it tries to reach equilibrium again, it has to flow over to the other side, just like the water, and make more products. So when more HF is added, oops, the hydronium ion concentration increases. You make more of it. So you put more of this in, you're going to make more of this. It's going to flow over that way. What happens to the hydronium ion concentration when more fluoride is added? How is that going to equilibrate? So again, think of the example up here. Which side of the tank, if you think we're starting here, which side of the tank are you filling up if you're putting in more fluoride? Tank B, right? Because fluoride is over on the right here. So if we imagine this is the left and this is the right, this is the reactants, this is the products. If we put in more products, we end up pushing over toward this side, right? So if we push over toward this side, that means that more of this is going to get reacted with, and that's going to end up decreasing. So if you add more on one side, you make more of the other. If you add more on the right side, you make more on the left side, which means the rest of the right side has to go down. So it always has to balance out. And then you can also think about removing things. So what happens to the hydronium concentration when fluoride is removed? If you remove the fluoride ion, what happens to the whole system? Like what's that? How's that changing the system? Is what? Yeah, you remove the fluoride out, which means the system has to compensate by pushing more over to that side. And so if it's pushing more over to that side, that means it's going to make more of both products, the fluoride and the hydronium. So there's going to be more hydronium in that situation too. So we can talk about a reaction being at equilibrium, and then we can put a stress on it, which means we change one thing from one side or the other, and the system has to readjust to compensate for that. And how it readjusts can affect your reaction. And this could be really, really important when you're trying to get a reaction to work. Like let's say you're not getting very good yield. It's not forming the products the way you want it to. One thing that could be an issue is maybe it's an equilibrium problem. Maybe it's going back and forth too much. So if you can remove the products as they're made, you can keep forcing the reactants to make more products because you keep changing that, that part of the equation. So that's how this stuff kind of works. Now what does this have to do with acids and bases? Well, since acids and bases are equilibrium reactions, we use equilibrium to define strong acids and strong bases. So there's a really big misconception about this. So I'm not even going to write it down, but we'll address it. That strong and weak has something to do with reactivity. That strong acids are the ones that are dangerous, that are going to burn you, that burn through the floors, all that kind of stuff. And weak acids are not, less reactive. And that's wrong. It's not that that's a wrong idea, but that's not how these things are defined. The strong and weak words in this in acids and bases refer to electrolytes. So how well they form ions in solution. And that's actually an equilibrium thing. So a strong acid we define them by saying they dissociate completely in solution. So what that means is if we put HCl in water, we're going to make hydronium and chloride, which is what results when the HCl splits up. So that's what we mean by dissociate. It splits up. And notice the arrow I drew there. So yes, it's true that technically every reaction has a little bit of forward and backwards, but in a strong acid, it's going to dissociate completely. It completely makes ions. So when we looked in lab the other day with the light bulb, the strong acid made that light turn on really, really bright because there were lots of ions in solution for the current to run through. So strong acids dissociate completely. They break up completely into ions. There's almost no equilibrium. Weak acids only dissociate a little. So HF is an example of a weak acid, hydrofluoric acid. When that reacts with water, actually, or when you put that in water, most of what you have is just HF dissolved in water. It doesn't break apart much. It doesn't form much hydronium. One way we can draw that is by having a really little forward arrow and a much bigger backwards arrow. So the equilibrium in this reaction mostly flows in the backward right to left direction. So that means that in that solution, when you put HF in water, you mostly have whole HF molecules that are dissolved, but they're whole. And a little bit, you have them broken up. Just a little bit will break up and dissociate and form ions. So that's why that's called a weak acid. Now, remember that that has nothing to do with danger or corrosiveness. HF, for instance, is one of the most dangerous acids that there is. It's kind of like the one that can like dissolve your bones and eat through floors, and you can't even keep it in glass because it eats through glass, so you have to keep it in plastic or steel. It can eat through rocks, it can eat through bricks, all that kind of stuff. But it's technically a weak acid because it doesn't dissociate in solution. It mostly stays together. Bases work the same way, but because bases are ionic compounds like sodium hydroxide, calcium hydroxide, it has to do more with their solubility. So there isn't, it's not so much this equilibrium rule, but the idea of the solubility. Are they breaking up and highly soluble in water or not? So we haven't talked much about bases in the Ka. Let's see, what do we got, about 10 minutes? So let's look at bases for a minute, since we've been focused mostly on acids. Most of the molecules that we're going to encounter that we're going to call bases are hydroxides. So things like sodium hydroxide, calcium hydroxide, potassium hydroxide, etc. There are other bases too, because remember, anything that can accept a hydrogen ion is considered a base. What makes hydroxides particularly good bases? Why do we think of hydroxides as bases? What do you get when a hydroxide ion accepts a hydrogen ion? You get water, right? So the reason these are such good bases is that if hydroxide ion reacts with a hydrogen ion, you get water. We know water is a stable molecule. Most of the things we're talking about are in water solutions anyway, so forming water is a good way to drive a reaction forward. So that's why we often see hydroxides as bases. There are other types of bases too. So one we saw earlier is ammonia. Which is a weak base. Ammonia acts as a base by accepting hydrogen from acids. So if ammonia reacted with HCl, let's say, it would form NH4 plus and Cl minus. So it would take the hydrogen from the Cl. So that's the way that ammonia can act as a base. Ammonia can also act as an acid. Ammonia in solution, in water solution, is technically a hydroxide. If we go back up to that reaction we saw earlier, there we go. If you look at that second reaction, when ammonia gets dissolved in water, it takes a hydrogen from water and becomes ammonium and leaves hydroxide. So when you dissolve ammonia in water, what you really have is an ammonium hydroxide solution. So it's still an ionic solution, even though it started with these neutral molecules. So ammonia is really, it's kind of like a hydroxide in water solution. All right, so that's strong versus weak acids, equilibrium. And so the next thing is to talk about the ionization of water and the pH and we'll finish that up on Tuesday because I don't want to get into that right now. So we'll stop there. No quiz next week. Lab Tuesday, and the lab from 2 weeks ago will be the report will be due lab 8, and yeah, then we'll have a quiz probably a week from Tuesday on acids and bases. So have a good weekend. If you want to wear your Halloween costumes on Tuesday, just make sure that they're lab appropriate, because you still have to follow the lab rules. But it's up to you. Shoes and all that kind of stuff. If you want to bring candy, it's also good.